Okay, now can you see my screen? Shared it. Do you see my screen and my voice? Yeah, Rohan, tell me. Rohan, you want to ask anything?
No, sir.
Okay. Can you see the screen?
Yes, sir.
Okay. So now let's start. So we were discussing about the frequency response of first order instrument. So I was telling that frequency response means that if for linear system, if you give a sinusoidal input, definitely as the output you will get a sinusoid, but the amplitude will be different. There will be phase angle compared to the input. So and those amplitude and frequency phase angles will change with the input frequency. So basically what we need to know that how amplitude or ratio of the amplitudes and the phase angles are changing with the input frequency. And when we plot these two, input frequency versus the ratio of the amplitude of the input and output, and the input frequency versus the phase angle, then we get two plots. Basically these two plots are called the frequency response of a system. Now, when we know the frequency response of a system, you give any sinusoidal, you just identify the amplitude, you just identify the frequency, and from these two plot, you go to that frequency, that input frequency, you will get the ratio of the amplitude, you will get the phi, so you'll know what will be the output of your system coming out of the system. Now, this can be looked at in bigger perspective. Suppose any input you are giving, and according to Fourier series, we know that most of the, I mean, almost every input can be decomposed with a series of sinusoidal inputs. So the inputs now becomes not arbitrary rather than summation of many sinusoidal inputs. And for individual sinusoidal inputs from the frequency response, you know what will be the output. And then suppose for all the sinusoidal inputs you get the output, you sum all the outputs, the resultant sum will be the output coming out from the system. So this is the for that particular frequency. So this is the way you could also determine the output if the input is not sinusoidal. So now let's come to the first order system. If you see our system is Q0 by Ki is K, Q0 by Qi is the K by I j omega or j omega tau plus 1. That means we have two parameters, K which is the static gain and the tau which is the time response, or sorry, which is the not rise time, which is time constant of the system. And if you calculate want to calculate the gain, that will be K by root over omega square tau square plus 1. And if you want to calculate the phase, that will be tan inverse minus omega tau. So the amplitude ratio will be K by root over omega square tau square plus 1, and the phase angle will be tan inverse minus omega tau. So the ideal frequency response will be for a zero order system or instrument, we have Q0 by Qi will be equals to the gain for any zero, but it is the first order, so no need to see that. Now let's see do one numerical. Suppose we are giving, that's what I say, that the input two sinusoidal inputs. So first sinusoidal input is the amplitude is 1. So 1 sine omega t or 2t, here omega is 2, you can see, and the next sinusoidal input is 0.3 sine 20t. So it is the input is the 0.3 and the sine 20 is the omega t. So there are two sinusoidal inputs, one having the omega 2, another having the omega 20, and it is applied to a first order instrument whose tau or time constant is 0.2 seconds. Since this is a linear system, we may use the superposition principle to find Q0. That means we calculate the individual output due to the first component and the output due to the second component, and then sum it, you will get the ultimate output. So if you want to calculate the output due to the first component, so that is amplitude is 1, and frequency is 2. So we know the output will be of the amplitude k by omega square tau square plus 1. So if it is k by omega square tau square plus 1, so k by omega will be equals to 2. So 2 square and tau square is 0.2, 0.2 square. So that will be 4 into 4.16 plus 1, and the angle will be tan inverse omega tau, where you have seen, you see tan inverse minus omega tau. So that will be minus omega tau. So tau is 0.2, omega is 2. So if tan inverse you can calculate, and you will get minus 21.8 degree. So your output due to the first input or first component of the input will be 0.93 K, and angle will be minus 21.8 degree. Now let us come to the second component, output due to the second component of the input, where amplitude is 0.3 and frequency is 20, omega is 20. So if you see the k by root over omega square tau square, so 20 square into 0.2 square, okay, that you will get q0 by qi, and you will get minus 76 degree if you calculate. So your ratio q0 by qi will be equals to 0.24 k into, and angle will be minus 76 degree. So the output will be sum of these two. So sum of the output for the first input will be qi multiplied by 0.93 k and angle minus 21.8 degree. We know that qi equals to 1. So q0 will be 1 multiplied by 0.93 k sine 2t minus 21.8 degree. You see phase angle we are adding, plus the output due to the second input will be amplitude 0.3 multiplied by 0.24 k into sine 20t minus 76 degree. So ultimately we will get the two output, and the output will be the summation of these two. And if we know the static gain k, we can put the substitute the value of the static gain k, and then both the sign you can add, and then you will get an output. So this is the way you can get output if the input is combination of many sinusoids. So that's why I mean to say. Now let's see if you have any query up to this point. Oh, it seems there is no query. Okay, so then let me proceed. So frequency response of a first order system is covered. So yesterday also, last class I discussed that the frequency response of a first order system will be some kind of contain one pole. So it will be initially for low frequency, it will be a pass band, and then when the frequency will increase, the pass band will gradually reduce. So it will become, signal will become attenuated, and the slope of the gain versus omega plot will fall with the minus 20 dB per decade. So that is the way. So first order system can act as a low pass filter, and and you can think about that if the input frequency you should know, and that should fall in the pass band to get the output, so that you can measure such input. So you need to know the approximate frequency range of the input, so that you can design the your first order system such a way that it falls in the pass band, or and output is not attenuated. Now let's come to the impulse response of first order system. So now let's see what do you mean by the impulse response. So you see the figure left hand side, this. So here you see that a input is present, where input is present for a time of capital T, and you see your input magnitude is a by t. So if you multiply, if you trying to see the area, so a by t into t, the area a will be area will be equals to capital A, and it will be a constant. It is not a function of time. So now this pulse, which we call as the PT in the figure A, and then this pulse width is gradually decreased. Let's say is, so this pulse if we give to some first order system, you will get some output. So this pulse could be the measurement. So now if we see that this pulse is width is gradually decreased, that means when the capital T, that means the width of the signal is gradually decreased. So, but the strength will remain A, because A by T into T will always be A. But what will happen? This width of T will be very gradually decreasing and height will be increasing, because if T decrease, A is constant, A by T will increase. So when T tends to 0, that means very limited period of time, this input is present, and the signal strength A remains constant, but the amplitude becomes very high, tends to infinity. So such a signal is known as the impulse signal, you know. So now you see how the signal, how the first order system may behave in presence of the impulse system. Now see, you see the figure B. Here a first order system is subjected to an input which is A by T and which time is T. So A by T and the time is T. You see the strength is capital A again, but during the period when this A by T is present, it might be kind of step input, you see, and then gradually it comes to 0. So for such input, the output of a first order system will gradually increase, and then as the time goes on increasing and there is no input of that system, this output will be gradually decreasing, and you can consider that in the second part of the B. Now you see if this width has changed very less, so T by 2, and then the height of the signal will also be increased by twice, because T has decreased to, so 2A by T, and then you see the width is changed, width is small and the magnitude of the signal is high. So for that small width, you see that the signal is going to rise for such time, and then it gradually exponentially decaying because there is no input. Now think about an idealized condition when the T tends to 0, so almost no time or signal is present, very infinitesimally small, and then the input magnitude will be very very high, uh, infinitesimally high, and then you see that infinitely high, and then you see that the signal, the output, then there is no signal, so output will start from an value and then it will gradually decrease to 0 as time progresses. So this is a typical impulse response. So how do you can calculate the impulse response? That is very simple. There are two ways you can calculate the impulse response. First is the Laplace transform way. What you can do, we know that the transfer function is k by tau is plus 1, and then the impulse response Laplace transform is 1. So you can multiply it 1 and take the Laplace inverse. You will get the output in time domain. Another way you could do that, you see the equation 3.171, where our time small t is acting in between 0 to capital T, and then we'll consider the small t which is greater than capital T. Now here you see tau d plus 1 into q0 will be equals to kqi, and we know kqi will be the amplitude and it will be the ka by t, and we can calculate the complete solution as q0 will be equals to ka by t into 1 minus e to the power minus t by tau. Now, if you see, this solution is only valid up to time capital T, because we consider small t in between 0 to capital T. So at this time we have, so Q0 at small t equals to capital T, we have Ka by T 1 minus e to the power minus capital T by tau. Now for the time when t tends more than capital T, our differential equation will becomes, right hand side will be 0 because there is no input. So it will be tau d plus 1, Q0 will be equals to 0. So Q0 will be equals to C to the power minus T by tau. Now this constant C could be find out from the equation, from the condition 173, where you will see that q0 at small t will be equals to 0 equals to this. So you substitute this, you will get c to the power minus t by t will be equals to ka by this, because there will be the output will be continuous at the time of t where it will reach, and that will be same as where it will start. So this k by t 1 minus e to the power minus t by tau will be equals to c to the power t. So from here we can calculate the C. So C will be like this expression 3.177, and finally Q0 will be equals to this C That means Ka 1 minus e to the power t by tau by e into t to the power t by tau by t to the power minus capital T by tau. So this will be the Q0. So ultimately we get the output at the Q0. So now here one thing is that we 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 we, we consider capital T is not tends to 0, it is some finite value, but in impulse response capital T will be 0. So here if you come to the equation 3.179 where capital T tends to 0, so ultimately our output will be the expression 178 where capital T tends to 0. So that's what we consider. So we write it here and we keep it this one out because as capital T is not here. So here we can see Ka e to the power minus small t by tau. This is coming, K is coming out, and limit t tends to 0, 1 minus e to the power t by tau by capital T to the power minus t by tau. This is a simple limit evaluation, and you can see for capital T tends to 0, this will be 0 by 0. So we can use the L'Hospital rule. So both the numerator and denominator we can make the derivative, and once we derivative we get the limit as 1 by tau. Thus we finally see that when this tends to 0, the limit will be 1 by tau. So what will be, so 1 by tau, and this term remains Ka e to the power minus t by tau remains. So what will be the ultimate output for an impulse response? That will be Q0 will be equals to Ka by tau. Tau is coming from here into e to the power minus t by tau. So you see if t is 0, so Q0 will be equals to Ka by tau. So it will start from Ka by tau. So here it is plotted. You see it is starting from Ka by tau. And then gradually it is exponentially decaying with the function e to the power minus t by tau. So ultimately we will get this type of plot in T. So impulse response will be will starting from some value which is Ka by tau, Ka by tau where A is the strength and tau is the time constant, K is the static gain, and then ultimately the signal will decrease exponentially. So this is the way we can prove it. This is the way we can say that what will be the impulse response of a first order system. Now if you see this one is plotted here, impulse response of a first order system, you see, so Q0 will be equals to, we have taken A equals to 1 and capital T is 0.001 tau, which is quite small compared to the time response or of the first order system. So ultimately we get Q0 will be equals to 100 K by tau 1 minus to the power T by T when T is 0 to T. So you see for that period this curve is sharply increasing to 1 very sharply and very short time, and then for capital T to infinity, what is it is starting from Q0 by K by tau, and it is slowly decreasing. So this is made in a computer where this 182 and 183, these two equations, we get the output Q0 when we substitute small t as a very small 0.001, 0.002 like that. All the values we can give, and the computer will give the exact the output, and that we can plot. So if we plot that, we'll see this type of curve. For the very small time it is sharply rise to 1, and then gradually it decreases slowly. So this is the kind of impulse response of a first order system. And tell me now if you have any query. Anybody has any query of this impulse response of a first order system? Okay, so let's go back. Nobody is asking anything. So what do we learn for the first order system? We learn about the step response. We learn about the, and what will be the impulse response. One thing I forget to tell. What will be the steady state error? You see, as t tends to infinity, it will be 0, and the input signal as t tends to infinity is also 0. So the output reaches to 0. So steady state error is 0. So there is no steady state error. So now you see, if we summarize this, we consider a first order system and we give a very typical standard inputs, which is step input. So we see that how the step input, step output for a first order system for step input is its exponential rise, and we have seen there is no steady state error because it rises to the values where the input is, or the gain multiplied the values where the input is. Now you see, you think about the ramp response. We give the ramp response, output also keep on increasing with slope, but at steady state there will be always there will be a gap, so there will be a steady state error, which is a function of tau. Now then come to impulse response. In impulse response, we give a impulse to a first order input. So these whatever input I am saying, this is a kind of measure end. So we want to measure such, and we want to know how the output will be, because that from there we need to know that what will be the input, although it is changing with time. So now for the impulse input, we see that the output of the output will be gradually decreasing and it will come to zero. Steady state error will also be zero. For the frequency response, we discuss in detail how any input can be decomposed with several sinusoidals, and as being a linear system, what will be the output of the individual sinusoidals, that we can know from the frequency response, and ultimately we can club together or add together to know the final output, overall output. And moreover, we have discussed that how the bandwidth is of the of a system is kind of remains in bottleneck in kind of measurement of some input varying, some varying input, because you need to know what the frequencies of the, or the tentative frequencies of the inputs, and accordingly you need to design a system so that the all the input passed and they don't attenuate or they lies in the bandwidth of the system. So, and otherwise the system will not, your measurement device will not be helpful. So you need to change different parameters in terms of spring constant and some other values. So in such a way we have discussed in detail. Now you may ask one question, that if your input is not a standard one, what you will do? Definitely your input may not be standard one. It may not be step, it may not be impulse or ramp. So then what you can do, you can do a few things. That if your input is not standard, first thing you can do, you can write the output for a non-standard input, and then from there you can, from the output, if you can calculate the input by the inverse Laplace transform, if you know the transfer function of the system, that is possible. Another thing you can do, the output you can decompose. uh, so output you can decompose into several sinusoids, and for each sinusoids you know the input because you know the frequency response, and then you add all the inputs, you come to know what the input is. And that is what our objective is. We want to know what the input is, or what the values of the measurement, which is changing with time. So with these notes, I conclude the first order response or first order instrument, or dynamic response of a first order instrument. Then I will move to second order instrument. Before that, I want to see if anybody has any query. Okay, so did you understand everything? So if you all of you understood that, then you let's start the second order system. Okay. So second order instrument now, first order instrument, I said it is good. It has some dynamic response, and then not all the system. If we get the zero order system, it is the best, but not all the system can be designed with the zero order system. Now all the system cannot be designed with a first order system. So by designing, you may get a second order instrument. What is the second order instrument? I'll come to know. So now you recall that the big equation where I gave a n dn q0 by dt n like this, and the right hand side b m uh, dqi dmqi by dt, that big equation what I wrote there. And from there, if we truncate, we assume that there is no zeros, so no derivative of the input, so that all the input derivative terms we remove, and we say that all the coefficient more which is starting from a3 a4, all those things are zero. So we have only the two coefficient a2 a1 a0. So our equation, that big equation, is truncated to this 3.189, where our second order instrument we can write as a dynamic equation, a differential equation, which can be written as A2 d2q0 by dt2 plus A1 dq0 by dt plus A0 q0 will be equals to B0 qi. And that is our the governing differential equation of any second order system. And this is a second order differential equation. And there might be more terms in right hand side which contains the derivatives of qi, but we assume that there is no zeros and all the derivatives are absent. And that may be in engineering instrument it may be valid, but there are many instruments which has the zeros or the derivative in the right hand terms. But for the time being, let's ignore that and start proceeding. So equation 3.189 is called a second order system because the order of the differential equation which can be used to model it is 2. So it is a second order system. Now, if you can look the equation 3.189, there are many constant. Okay, so at least three constant you can see. Uh, in fact, in the equation you can see the four constant a2, a1, a0, b0. But what you can do, you can also always divide the both left hand side and right hand side with the a0, and you can think about the ratios at the constant. So you have the three constant. So first, let's divide it with a0. So right hand side, what we will get? We will get b0 by a0, and that is k, and that is called the static sensitivity. Static sensitivity means when dynamics is not present. Always I discuss the instrument output reaches the steady state, then the gain output by input will be the static sensitivity. That means under static condition, what is the sensitivity? And you know the sensitivity means the gain output by input. Now, if you see that a0 by a2, that is a kind of ratio of two constant, and if you take that can be defined as the omega n square, or the omega n is the root over a0 by a2, and that parameter is known as the undamped natural frequency. So its unit is radian per time or radian per second, and it is called the undamped natural frequency. If there is no damping, you give some excitation or step input, the frequency this system will oscillate, that is the a0 by a2. We will come it later, but for the time being, this is the meaning of the undamped natural frequency. And you see, we define there remains another terms which is a a1 by a0, and we defined in a different way to relate it with the physical things. So you see that we defined zeta as the a1 by 2 root over a0 a2. So which is nothing but a function of omega also, and the constant. So this zeta we call the damping ratio, and it is a dimensionless, and we wrote in such a way this constant so that our equation 3.189 becomes d square by d means s, you can consider. So s square by omega n square plus 2 zeta s by omega n plus 1 into q0 will be equals to ka into qi. So the operational transfer function is thus, we can write q0 by qi will be equals to k by s square by omega n square plus 2 zeta s by omega n plus 1. More frequently, we write k into omega n square divided by s square plus 2 zeta omega n s plus omega n square. If we multiply both numerator and denominator with omega n square, you will get such. So this is a very standard way of writing a second order transfer function. Whenever you get a second order transfer function, you write in this standard way. What is that? q0 by qy equals to gain k omega n square by s square plus 2 omega n zeta into s plus omega n square. If you can write in this way from the coefficient of that transfer function, you can easily determine the static gain k. You can easily determine the omega n natural frequency of oscillation. You can determine the zeta, which is the damping coefficient, And from there, you can quickly have an idea how the system will behave when you give some input. So now, okay, let me see if any query you have. Okay, still now you don't have any query. So let's go. Then so if you see the second order instrument, we have a or many instruments are in second order in nature. So you see in reality, so you see the galvanometer, that you know it is a second order instrument. You see the voltmeter, analog voltmeter, ammeters, those are also second order instrument. You see that spring balance, what is given in this figure in this slide, that is also a second order instrument. So many instruments are, you can see that the displacement acceleration sensor or something, those are also. So the many instruments are of second order instrument, and those which are not second order instrument are frequently approximated to a second order instrument. So second order instrument is very important to understand and read. And in fact, we'll read up to second order instrument. Beyond that, third order, fourth order, we will not read. So if you see that the second order instrument, one example of it, you see this is a kind of spring balance where you have seen there is a piston, there is a spring, there is a scale. So if you put pressure or if force on the uh, piston, which has some elongated surface on the top, so what we can see that this will squeeze and the spring will give the opposite force, and ultimately at one point of time it will stop to squeeze, and so this is kind of deflated and stay there. So you can mark it or calibrate the scale. So if there is no force, the piston will not squeeze or will not be shortened by anything. So that point you mark at 0, and you give different known force, and the spring will be squeezed, and you mark it. So that becomes your calibrated instrument. You take the instrument and then you see that if you give the input force to that instrument, it will be damped or it will be displaced, and you read the displacement over the scale to directly know what will be the your force or your weight. That can easily be calibrated in weight. So now this system, you can see it has the input, which is the force or weight. It has the spring, which will try to counterbalance the input. It may have the damping. You can see that it is emerged in a damped environment, so it can have a damping. So there might be an S term. So when you have seen that there will be damping, there will be restoring force. So very frequently that system will become a second order instrument. Now if you try to write the transfer function using the Newton's law, so you'll see that input will be Fi, and if there is a damping force, the the force opposing the input will be equals to the constant B multiplied by rate of change of x0 or the velocity. That is the damping, it says. So if the velocity changes, the damping generally oppose the restoring force. If there is no velocity change, if there is no velocity, sorry, not velocity change, Poisson change. If there is velocity, there is damping force opposite. If there is a velocity, the damping force opposite. So B, and that is a proportional to the velocity. If your velocity is more, damping force will be more. So that will be B dx0 dt. And then you see that you have a displacement and you have a spring. So when displacement occurs on the spring will exert the opposite force, and that is proportional to the displacement. So the opposite force will be Ks, which is a constant, into x0, and ultimately the resultant force then becomes Fi minus B dx dt or dx0 dt, whatever you want to say, minus Ks into x0, and this force will be M, capital M is the mass, into capital M is the mass, into d2 x0 by dt2. So this is the Newton law of motion, and from there if you write in the Laplace domain, ms square plus b into s plus ks into x0 will be equals to fi. So that is the kind of, so now if you see that the left hand side has a s squared term, so it is a second order instrument. Always I said that if there is a damping and if there is a spring action, or if there is action opposing force which is proportional to velocity and the opposing force which is proportional to constant, proportional to displacement, you will always see this is a second order instrument. So now from here you see you can write it properly, and your gain, static gain, will be equals to 1 by ks, because you need to divide both the side by ks, and then your omega m will be ks by m square root, the way we defined on the left hand side you can see, and your zeta or the damping coefficient will be b by 2 root over ks into m. So ultimately your transfer function will become that x0 will be equals to fi into omega n square divided by s square plus 2 zeta omega n s plus omega n square. So that is the transfer function, and there are three constants. So you see the first order system, zeroth order system, there is only one constant which is static gain. First order system there are two constants which is static gain and your time constant, and in the second order system you see you have the three constant which is a static gain k, another is a natural frequency of oscillation omega n, and another is a damping factor zeta. So this is the way you can define a second order system. Let me see if you have any query up to this. Okay, let's proceed then. Now if you see that the next slide, so gradually we need to go that how it will be the output for the step input, and so it is very important for to know. So maybe you will be reading this in control system class, and you will be deriving all the output due to the step input. So I am skipping the derivation, so I am taking the final results. Maybe you can think about from control class. If this is not derived in control class, you can ask me, I can derive it. It is not very difficult. In fact, it is very simple to derive. So now what is our objective? Our objective is to know what the output will be when you apply some input, step input of a second order system. Or in the opposite way, if we know the output, we need to know what the step input is. That is our objective is, because we are reading the control, not reading the control system, we are reading the instrumentation. So if you see d square by omega n square plus 2 zeta d by omega n square plus 1 equal to q0, and the input is kqis. So we need to solve this differential equation either in the time domain or in the Laplace domain or frequency domain. Now if we solve in the time domain, that is also highly possible. There are two initial conditions. So at t equals to 0, that means the starting point, we don't have any output because the input is also 0. So q0 will be equals to 0. This is the first initial condition. And the second initial condition will be at t equals to 0, our velocity q dq0 change. There is no input, no output, and there is no change of output. So dq0 by dt will be equals to 0. So with these two initial condition, if we solve the equation 3.200, we will see that there are three different solutions based on the value of zeta. Now the zeta value can be, the zeta value can be less than 1, it can be equals to 1, it can be greater than 1. Okay, so based on that our solution will change, because the reason is that when you see that the root of this equation, based on the zeta value, the equation root of the equation will change. Sometimes it will become positive side root, sometimes it becomes negative, sometimes it will become complex imaginary roots. Okay, complex root, set of complex root, right there. So for that reason, for different zeta we'll get the different solution. So that's what we need to think about the zeta before getting the solution. Okay, so that's what I said. So zeta could be less than 1, zeta could be greater than 1, zeta could be equals to 1. Okay, and obviously zeta could be equals to 0 also when there is no damping. So let's see that when the zeta, I told you that when zeta is greater than 1, that is called the overdamped system. And for that, we'll get a solution of equation 3.202. So Q0 by KQIS, you can multiply K on the right hand side also. So it is the output by input equation, which will be, the expression is very big. You can see there is a zeta plus root over zeta square minus 1 divided by 2 root over zeta square minus 1 into some bracket into e to the power something into omega t plus the same thing e to the power something into omega t plus 1. You see that 1 is there. So it is a overdamped system. That means it is not an oscillatory. It will always be less than 1 as the t keep on increasing. And when t is very very high or t is infinite, you will see that the first two terms will die out because you have t there, and always the both the terms are e to the power minus something there, because zeta square minus 1 root over will be always less than minus zeta. So always it will be to the power minus term, and these two will die down and ultimately it will reach to 1. But you need to wait for long time, so that as time keep on increasing, the output will becomes 1. So this is a overdamped system. So in our application, this has a limited application. Now let's come to the equation 3.203. So which is quite short equation. Q0 by Qis will be equals to minus 1 plus omega nt into e to the power minus omega nt plus 1. Here also you see that as t tends to increasing, the output keep on increasing. It never overshoot. And when t tends to infinity, these terms will go down and it will reach to 1, or k, rather k, because k is static gain. So if we divide by k, it will reach to 1. If we don't divide by k, it will reach to k, because it is a static gain. This is called the critically damped, and this system is kind of also less limited use. The most frequently we use a system which is called the overdamped system, which is 3.204. Let's see if there is a query. So if you see that, so this is a kind of over under time system, where you see there is a sine terms and there is a phase, and there is a amplitude also plus 1. So when t goes to infinity, definitely this amplitude is equal minus zeta omega in t, it will be 0, and this will reach to 1, fine. But before reaching to 1, which is a steady state, you will see there is a sign which will predominate, so it will keep on oscillating. So it will start from 0, because at t equals to 0 it will be 0. It will start from 0, and then from 0 it will keep on increasing. It will oscillate. Gradually the oscillation will die down, and then it will settle to the value 1, which is known as the underdamped system. The underdamped system will be when zeta will be in between 0 to 1. If zeta is near 0, the damping is less, so oscillation is more. When zeta is near 1, the damping is more, oscillation is less. When zeta equals to 1, it is a critically damped. It will never shoot up. So slowly keep on increasing, and exponentially it will increase to 1. And then if it is greater than 1, it will also increase, but much slower rate than the critically damped system, and after very long time it will reach to unity. Another thing which is not written here, that is undamped system, there zeta will be equals to 0. If zeta will be equals to 0, you will see that s square plus omega n square q0 will be this. So there will be no damp, so it will start from 0 and it will keep on increasing and then decreasing. So ultimately you will get a sinusoidal output for a no damp system, because there is no damp. So these four type of things can happen when you give a step input to a second order instrument. Okay, fine. So time is up. So tell me if you have any query. So till now you did not ask any question. If you have any query, you can ask. I'm just waiting a couple of minutes. Okay, fine. So if you have no query, then what we can do, we can close here. Tomorrow we have two classes. So that tomorrow class will start from maybe 9 to 10 and 10 to 11, two consecutive classes I'll take. And then Wednesday there will be no class. So then let's meet tomorrow at 9. So 9 to 11 I'll take two classes, and we'll keep on discussing more about the second order system. So now you can leave, you can end the class here. Thank you all of you for attending the class. So tomorrow we'll meet again.